Today we're doing fluids in physics and pirates. We like us some fluids. Of course, I meant ocean water there with my fluids. Yeah. Well, we have a whole bunch of formulas for this section. The good news is that each one's pretty straightforward except for the very last one, and so in some ways this unit gets a little easier. Our first one is Archimedes' principle, right there. Archimedes' principle says that there's a force for anything that's in a liquid. That's called buoyant force. And it's an upward force, and it equals the gravitational force of whatever it is you're displacing. And so since it's a gravitational force, it starts with mg. But since we're dealing with liquids, we don't want to really deal with total masses. We want to change mass into densities and volumes, because that allows us to tell when things float and when they don't. And so we use the equation that density equals mass times volume. We rearrange that to mass equals density times volume, and a pretty specific density and volume. The one that we want is the density of the liquid times the volume that is underwater. So like if you have a thing, this is the volume underwater, not the whole volume, just the part that's underwater, and the density of the liquid is the density of this, not the density of the object, but the density of whatever it is you're displacing. Oh, there's a weird Greek letter here, right? This, oh, that's a bad one. This is a rho. Like row your boat, R-H-O. That's really hard. My pen's not working that way. A little later I have it printed out. Rho is the density, and it's a P with a little tail on it. And Microsoft Word won't do it very well, but here, let's give it a little tail too. But that's how Word does its rho. And there are two rhos that we use a whole bunch. The rho for regular water is 1,000 kilograms per meter cubed, and salt water is 1,025. Notice that's different than the one we use in chemistry because we're dealing with meters cubed and kilograms instead of grams and liters. When we're dealing with buoyancy, it changes the amount it seems like something weighs. And if you remember apparent weight back from forces, apparent weight is whatever our matching force is. In this case, if we have a spring scale and we have force of tension, oh, I think actually in this one I called it force of spring, Fs. Fs. My pen's not working very well today. I don't know what's going on. Fs is my matching force. And I have gravity going down, I have buoyant force going up, and notice that if buoyant force is going up also, my weight, apparent weight, the Fs one, the tension force, is going to be less because buoyant force takes away some of that force. And so that's why you feel like you weigh less when you're in water. And it's just a really easy free body diagram for forces to find that apparent weight, but sometimes it freaks people out. Don't let it. If we have a cube that's in water up here, there's one force on it we know is gravity. The other force we know, there has to be another force because it's not moving up and down, and we know the other force now is buoyancy. And so I make a little free body diagram right there. Buoyancy goes up, gravity goes down. But notice, those are both gravity forces. And so when we set them equal to each other, it's essentially mg equals mg over here. And since we're dealing with liquids, we don't want to have this m or the m that would be there, so we put density times volume for both of them. They're a little different though. The gravity one is going to be the density of the object times the volume of the object, so that's this density times that volume object. And then the density here is the density of the fluid, and the volume is underwater, the part that's underwater there. And notice that when we do this, the gravities will cancel. And if we put like terms together, we can say that the density of the object divided by the density of water, because that's my liquid, is equal to a volume underwater over the volume of the object. So that says that if I have an object that has a density of half the density of water, half of it will be underwater when it's floating. A third the density, a third will be underwater. And so we have a nice, easy relationship there. That's one of the reasons why we use that density times volume business. We like to use density instead of mass with liquids, and we like to use pressure instead of force. It's because when you put a force on a liquid, it make the whole liquid move since it's a liquid. When you push on one side, it doesn't go make the whole thing move as a block like solids do. What it does is it puts pressure on all of the liquid. And so pressure then becomes our thing we use instead of forces for liquids. And pressure is the force divided by the area. So like if we have a tube like this, and this is my area, and I apply a force on that whole area, it makes the pressure inside go up by force over area. And it turns out that when we have a closed system, that pressure, which is force times area, is applied everywhere in the surface. So once we give it a pressure inside that, that pressure is being applied on every surface that's in there, not just on the one that we put it on. And that allows us to do something called hydraulics, and lets us go to this really cool picture. Here we go. If you ever gone in to get your oil changed, you notice they have this big old machine that will lift up your car. And they use hydraulics to do that. What they do is they have a really small tube over here, and they put a small force down on it, 5 newtons, and it's on a really small area, 25 centimeters cubed, which is 0.0025 meters squared, not cubed, squared. And because force over area equals force over area, that small force on a small area, if we make a big area over here, it gives us a big force. So the force 1, which was 5, over the area 1, which is 0.0025, has to equal the new force over 4. And so we get 20 equals 0.0025 F2. So we take 20 divided by 0.0025, and we get a gigantic force, 8,000 newtons. So you can lift a whole lot by pushing down really, really small. Now, in this picture, they're saying that a person does it, and they used to, but now they use electric machines. But you can see how there's a multiplier there to get a really giant force. Now, we know you can't get something for nothing, right? And so this seems like you're getting something for nothing, but it turns out that it's not force that is conserved. We know it's energy that's conserved, and the energy that comes from force is work. And so work equals force times distance. And so we know that if we have a small force of 5 times the distance 1, it's going to be equal to 8,000 times distance 2. And so we know that this is going to have to be pushed a whole lot to get that to go up a tiny bit. Now you get a huge force, you can lift a giant car, except you're going to have to push a whole lot down on that little piston. That's why when people used to do it, you have to go over and over and over and over again to make the car go up a tiny, tiny, tiny bit. This next equation tells us how pressure goes up when we have a bunch of water. So if we're underwater, a whole bunch, let's say we're going to call that height, this tells us what the pressure is going to be down here. That's the P down here. P sub 0, which is right here, is what it is at the top of the water. And then rho is the density of the liquid that you're going through, and the height, and we know what G is. And so basically the lower you get, the higher the pressure is. And the weird thing about this is that it doesn't matter how wide it is. If we have a really narrow thing, and we're still looking for the pressure down there, and we have that height, it's the exact same thing. We just need the density of the liquid times the height. And that allows us to do some kind of weird things, and we'll get to that with some of our flash demos. Here's a quick demo problem on that, just so you can see. Up here at the top, it's 1 Pascal. No, sorry, 1 atmosphere. But to get to pascals, we have to use a conversion factor. 1 atmosphere equals 1.013 times 10 to the 5th pascals. And we want to be in pascals, so we're in meters and we're in newtons. And so when we do this actual problem to find out the pressure, if we go down 250 feet, we take this P sub 0, which is 1 atmosphere, but is actually all that big number instead, times the density of seawater, because it's Galveston, that's seawater, times G, times 250. Not sure why I put that on the line below it, but it's 250. We multiply it out, and we get a really, really big Pascal number. We could divide by this again to get in atmospheres, but usually we just leave it in pascals. And so, pretty easy problems, these. Arrgh, pirates do not buy their snacks. They steal it from their kids' Halloween candy. In order, the ones that I steal from his candy first. Snickers, oh, that's backwards. Snickers. Reese's. I can't get it to go the right way. Any other kind of chocolate. Steal some chocolate. You're a pirate. I'm a pirate. Let's do it. Our next formula for a particular situation are called continuity. I like to say continuity is put your finger over the hose equation, because what this says is that if our area gets smaller, things have to go faster through them. Because liquids don't compress, the same amount of liquid has to go through per second either way. So our basic equation is A1V1 equals A2V2. Pretty easy. These get a little complicated though, because sometimes they'll tell you how much volume goes by per time, and you have to set that equal to AV. Or they'll say, what is the flow rate? And you have to know flow rate means A times V. But essentially, if your little brother is making fun of you because you had to wash the car, and they get to play around, and they're going, nah, 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 I don't have to do it. You take the hose, which you can't spray them with without it, stick your finger over it, lowering the area, making the volume, lowering the area, making the volume go up. You can spray them, and then you get in trouble, and it's really sad, and I don't like it very much. Okay. All the other formulas for this chapter are pretty specific. Bernoulli is the one for anything else. And Bernoulli is essentially just conservation of energy for liquids. So instead of mgh here, we use rho gh. Instead of 1/2 mv squared, we go 1/2 rho v1. Instead of saying work on each side, we take pressure on each side. We have to pick 2 points, like I always did in any energy. We have to have a 0 point for our heights. It's essentially just energy for liquids. And so we look for changes in pressure, velocity, and height. If we have 2 of those things changing, we can use Bernoulli. Since Bernoulli has a couple of them in there, we're going to do a couple examples since it's catch-all. And the first one is when we have an open container with water spurting out somewhere. And wherever it spurts out is going to be 1 over 2 points. The other one's always going to be the top of the container. So that's my 1, and that's my 2 right there. And so then I have to set a 0 point. In this case, since they're both heights are measured from the ground, I make that 0. I could make where this comes out 0, but since they measured them there, I did it that way. My first step is to see what things cancel, because in Bernoulli, lots of things always cancel. That should definitely be in your notes. The first one, both of these are at atmospheric pressure, so those 2 cancel. I know that this stuff here, compared to the stuff spurting out really fast, is not moving much. It's an approximation, but I'm going to say that's not moving at all. So this V1 goes away. Use a lot of approximations in Bernoulli, so make sure and write that down in your notes. And then I put like terms together. Down here, I cancel out my rows because I have a row and everything. And then I have this, then I put like terms together. I get V2 equals 2G times H1, H2. I get the 2 by multiplying by 2 there, and then I will get my V there. And once you cancel things out and approximate, it's usually pretty straightforward in Bernoulli. It's the canceling out that takes some thinking. Another Bernoulli example is a syringe. Now a syringe, we push on this side and we have a certain big area there. We have a small area here and the stuff spurts out really fast. And again, we're going to say this velocity 2 is really fast compared to the 1, and we're going to approximate the 1 to 0. This time the pressures are different, so I can't get rid of that. But this time, since it's horizontal, all the heights are the same. So we're all going through at this height, and so my heights cancel. So I canceled a bunch, I approximated this one. The other thing I have to do is realize that they both start at atmospheric pressure. So P2 is atmospheric. P1 I have atmospheric plus I put a force over an area. So I cross that out and I put this in instead. And since I have P2s on both sides, this ends up just being force over area equals 1/2 rho squared. Then I can just put my force, my area, and solve for my V. Again, once you cross them off, it's pretty easy. This one has that weird thing about pressure is force over area. So this kind of problem here is a pretty complicated one. We have a pipe that's getting smaller but also raising in height, and it's going to change its pressure. So this one we have to do continuity and Bernoulli. We'd first do A1 V1 equals A2 V2 using the area change to find the change in velocity. So they give us everything except for V2 and we solve for it. And then that V2 goes into a Bernoulli problem. I'm going to leave that to you since it's on our quest tonight, but realize that it uses that plus the P plus rho GH plus 1/2 rho V squared equals itself. Time for some chemistry review. We get to use PEVNERT, and I know you remember PEVNERT, and PEVNERT is your friend. We love PEVNERT. I love PEVNERT. PEVNERT is just pressure times volume equals the number of moles times the gas constant times the temperature. And when you did chemistry, these were the units you used over here. Now in physics, we like to use the same units for everything for all year, and so we're not going to use liters, we're going to use meters cubed, we're not going to use atmospheres, pascals. That changes our constant a little bit. So if you memorize the constant for chemistry, you're going to have to use a different one. We can use this PEVNERT a lot of different ways. We can, if we know everything in there except for temperature, or everything except for volume, or everything except for pressure, we can just plug the numbers in and solve. But really what we use PEVNERT for is we put PEVNERT over PEVNERT. Notice if we do that, our n's and our r's are both constants, and so they cancel out. And so we get right here what's called the combined gas law, which is the same as this up here, just moved around a little bit. But, for instance, if the volume stays constant, we can cancel volumes also, and we get Gay-Lussac's law. Or if the temperature remains constant, we can cancel the temperatures, and we can get Charles Boyle, I don't know, all the chemistry stuff you had to memorize. But we don't have to memorize it now. All we have to know is PEVNERT. PEVNERT is our friend. So if there's a change in pressure or temperature and something stays constant, then we plug it into PEVNERT over PEVNERT, and we get our lovely answer. Make sure your temperatures are all in Kelvin, 273 plus Celsius. Be a contemplative pirate as you go off and attack your quest. Take your quest. Get your gold, which is your